Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspired Teens Grade 12 Physics/Chemistry, where in today's lesson, we'll be continuing with chemical equilibrium. Okay. Last time we started off equilibrium graphs. Okay. We discussed temperature change and concentration change, which is where we ended. And now we will start off discussing pressure change. Okay. So these are already drawn in, but it's fine. I shall explain them. Let's have a look. Okay, let's just revise TCP one more time. Okay, this is the TCP that we went through, meaning the changes in temperature, concentration, and pressure. So we said that when temperature increases, the endothermic reaction is favored. When temperature decreases, the exothermic reaction is favored. Concentration increases, the other side is favored. Concentration decreases, the same side is favored. Pressure increases, less mole side is favored. Pressure decreases, more mole side is favored. Just note that there's a pressure decrease by an increase in volume, and pressure increase by a decrease in volume. Okay, just keep that in mind, as well as gradual, rapid, and rapid. Okay, so as you can see, right, we discussed what that means. So the first part is the reaction initially occurring. The second part is equilibrium is established. And the third part, at all the T2s, right, what happens is that there is a disturbance or a stress acting on the system. Okay, and what actually happens is the system counteracts according to Le Chatelier's principle, because that's the definition. When equilibrium in a closed system is disturbed, the system will counteract the disturbance by favoring the reaction that opposes the disturbance. So that's always what the system tries to do. So at all the T2s, what happens thereafter is actually Le Chatelier's principle. Okay, the system is counteracting that stress. Okay, so in this case, as you can see, for all temperature changes, it's gradual changes, and according to which reaction is favored, we would see a product increase, decrease, or a reactant increase or decrease. Okay, then we discuss concentration, and in concentration, there's also gradual, but you see the main where we say rapid, where we mentioned rapid is here. Right, you can see that this rapid increase in whichever concentration was increased, and then of course whichever reaction is favored, it determines this. Okay, and then here, whichever one was decreased in concentration, we see a rapid decrease in that, and then the favoring we can see take place here. Okay, now we're going to discuss pressure change. Okay, so as you can see, reaction taking place, equilibrium established. Now we have, I need to, sorry, 1 second. Okay, so like I said, okay, so we have an increase in pressure. Okay, so by the way, let me get my notes out actually. Okay, we have an increase in pressure by a decrease in volume. An increase in pressure by a decrease in volume favors the less mole side. The side with less moles, meaning the reactant or the product side, whichever of the two has less moles, that side is favored. Whenever there's an increase in pressure, the side with less moles is favored. So let's go to our reaction and let us determine which side has less moles. Now, remember, for this, we only consider the molar ratio of gases, only of gases. We consider only the molar ratio of gases. Okay, so in this case, we look at all three are gases. So here we have 1 plus 3, which is a 4:2. So the molar ratio of the gases here, 4 on the left-hand side, 2 on the right-hand side, because here it's 1 plus 3, which is 4, and here it's just 2. Okay, so now which side do we have to favor again? When there's an increase in pressure by a decrease in volume, we will favor the less mole side, the side with less moles. So we need to favor the right-hand side, which is the product side. If you want to favor the products, you have to favor the forward reaction, if you remember correctly, right? Reverse reactant. So if you want to favor the reactants, you favor the reverse, or the reverse favors the reactants, and therefore the forward favors the products. We need to favor the less mole side, which in this case is the product side. So we have to favor the product side. In order to favor the product side, we need to favor this reaction that creates products. The reaction that creates products is the forward reaction. Okay, so we need to favor the forward reaction. So What you'll notice first, before we consider any favoring, right? Because remember that this is Le Chatelier's principle taking place, having effect. Okay, LCP. So before any favoring occurs, what you will see is a rapid increase in the concentration of all three reactants. You will see a rapid increase in the concentration of all three reactants. That's why we discuss concentration. When there's a pressure stress, that concentration versus time change, we consider it as rapid. Okay, because the pressure increases, actually the concentration of all of the substances increase immediately. It kind of makes sense, right? Because imagine we have this little container, right? And now all of a sudden we decrease the size of the container. So initially we have a big container, okay, and it's containing all of our reactants. And now all of a sudden we just decrease the size of that container. What would happen is there'd be an increase in the amount of pressure that exists in there. So it would increase the concentration. Remember, concentration is like the amount of particles per unit space or per unit volume. Okay, so because the volume is less, right, we have a higher concentration. So it would increase the concentration of everything rapidly. Okay, so that's why we see this rapid increase in all the concentrations. Okay, and now after the rapid increase, we can discuss, remember, according to Le Chatelier's principle, the forward reaction was favored. So if the forward reaction was favored, what can we expect? We can expect an increase in the products and a decrease in the reactants. Is that what occurs? We have our product, which is NH3. We can see its rapid increase. Okay, and we also have, I need to add a new color, 1 second. I cannot match the colors. I guess that's close enough. Okay, so what I need to do is, no, that's not. Okay, yes, the forward reaction is favored, and so as you can see, the product increases and the reactants decrease. Okay, that's the main thing. Okay, I hope that makes sense. So we see rapid increase in the concentration of all three reactant and product. Okay, because of the decrease in volume, sudden. Okay, and because the forward reaction is favored, because an increase in pressure favors the less mole side, which in this case has to be the product side, which has to be the forward reaction. That's how we see the increase in products here and the decrease in reactants. Okay, cool. Let's move on to a pressure decrease. Remember, it's a pressure decrease by an increase in volume. So remember, according to Le Chatelier's principle, a decrease in pressure favors the side with more moles. Okay, so the decrease in pressure by increasing the volume favors the side with more moles. The side with more moles here is the reactant. If you want to favor the reactants, you favor the reverse. So therefore, the reverse is favored. So before we see any favoring occurring, what happens is we can see a rapid decrease in the concentration of both reactants and the product. A rapid decrease in the concentration of everything. Because there's a decrease in pressure, the concentration of each thing would also therefore decrease. Okay, then once we see the rapid decrease in everything, then we can see the reverse reaction being favored. Remember, when the reverse reaction is favored, we would have an increase in reactants and a decrease in products. So here we can see the increase in both reactants and the decrease in the product. Okay, if you guys have any questions, please let me know. If you want me to explain that again, please let me know. Okay, but yes, that's essentially the pressure change graphs and how they look when we have an increase in pressure, when we have a decrease in pressure. Okay, remember, this rapid increase and decrease are only for gases, because they're only affected by gases. So that rapid decrease in concentration would affect gases. Okay, that's important. Okay, so those three: temperature, concentration, and pressure graphs done. Let's have a look at rate versus time graph, which is where things get a little interesting. Rate versus time graphs. Firstly, we're going to look at, okay, so we have the same reaction, right? This Haber process. And same, I don't know if we're going to use this, but probably 4:2 molar ratio of gases. forward is endo. Let's copy this. Okay, forward is exo, sorry, reverse is endo. Okay, and yeah, we have that, whatever. Okay, so same reaction. Now we're going to look at the effect it has on the rate versus time graph. So we have a temperature change. When there's a temperature change, we need to always remember endo is affected more. So remember, we have rate versus time graph. Okay, here we have the rate of the forward, rate of the reverse meeting in the middle to become the same unit, the same value of rate. So we remember we start off with a high amount of the forward reaction because the rate of the forward reaction is initially high because there's a high concentration of reactants. So since there's a high concentration of reactants, the rate of the forward would be high. Thereafter, once we start increasing the amount of products we form, the rate of the reverse increases, right? And then the rate of the forward is decreasing because slowly we are using up more and more reactants until we reach the same rate. And that is known as chemical equilibrium. So in all of these graphs at T1, chemical equilibrium. I can actually just steal it from here. Because why not say? Okay, so at T1, what happens is chemical equilibrium is established. Okay. Okay. At T1, chemical equilibrium is established. At T2 is where the stress or disturbance happens. Okay, and then we'll consider T3 as well. Oops, can I get rid of that? Okay, that should be fine anyway. Okay, at T3, we'll see that chemical equilibrium is reestablished, but we'll put that in later. Okay, so with all of these graphs, I'm only going to write it for the first one. At T1, chemical equilibrium is established for the first time, right? Between T0 and T1, what happens is the reaction is occurring, right? Initially. At T1, chemical equilibrium is established for the first time. And then we have, of course, here we have equilibrium, right? And then at T2 is where the disturbance or the stress happens. And in this case, our stress is what? Our stress is an increase in temperature. Our stress is an increase in temperature. So let us steal this again. Sorry, 1 second. And let's put it here. And that's not great. Sorry. 1 second. How? Why is that happening? Okay. Sorry. Okay, there we go. Didn't take too long. Okay, so yes, an increase in temperature. We need to remember that an increase in temperature favors the endothermic reaction. Okay, favors the endothermic reaction. Okay, but is that piece of information useful? No, it's not. It is not. So what happens is, okay, so this is why the rate versus time reactions are a bit more tricky because they don't all exactly follow this. Okay, they're not as easy as following these guidelines. Okay, they each have their own individual aspect that affects them. Okay, each one: temperature change, concentration change, and pressure change. Now, the first thing, okay, for temperature change is that both reaction rates increase. Okay, this is important. Both reaction rates increase, but the endothermic reaction increases more. Both reaction rates increase, but the endothermic reaction increases more. Okay, so what you need to remember actually, okay, we'll get back to that. So let's do that change, right? Both reaction rates increase. So the forward reaction rate would increase. Okay, the reverse reaction rate would also increase. Let's sort of do this. Okay, so firstly, our reverse reaction rate increases. I hope you can see that. Maybe we can go to 0.3. There we go. Let's do this. Okay, so the reverse reaction rate increases, as you can see. Okay, and the forward reaction rate also increases, but the endothermic reaction increases more. And in this case, right, in our specific example, the endothermic reaction is the reverse reaction. The endothermic reaction is the reverse reaction. So therefore, because endo increases more, reverse increases more. And that's what we see here. The purple one is the reverse and it increases more. Okay. And then what happens is both reaction rates, okay, whichever one is higher, would decrease to form equilibrium. And whichever one is lower would increase to form equilibrium. I don't think we're going to get perfect. So for now, we just, just happy with that. Okay, so that's essentially what happens, right? So firstly, let's go through this again. It might be a bit confusing. There was an increase in temperature. How does an increase in temperature affect the rate of reaction graph or the rate versus time graph? So both reaction rates would increase. Okay, because remember at T2, the disturbance occurs. So at T2, both reaction rates would increase, so the forward and the reverse. But whichever one is endo always increases more. Okay, so in this case, the reverse is endo. So the reverse, the rate of the reverse reaction increases more. And we can see that by the purple one, equilibrium is established. And then when the change occurs, the reverse reaction rate increases more. So both increase, but reverse increases more. And then whichever one is more and whichever one is less, they always meet in the middle. Okay, the rate of the forward, rate of the reverse, they meet in the middle. Okay, and they form what kind of looks like a duck. Okay, it's not important, but it is. Okay, so that's the temperature increase. Let's have a look at the temperature decrease. Okay, and then thereafter, let's talk about T3. Sorry. So at T3, what happens? You can guess. Chemical equilibrium is re-established. At T3, okay, chemical equilibrium, that's not going to move, is re-established. Okay, once the stress is dealt with and it's counteracted, the system counteracted the stress. Okay, chemical equilibrium is re-established at T3. Okay, I'm only going to do all these annotations for the first graph. They apply for the rest of the graphs. Right, let's have a look at temperature decrease. So when there's a temperature decrease, okay, what happens is for rate of reaction graph, okay, both reaction rates decrease, but endothermic reaction decreases more. Both reaction rates decrease, but the endothermic reaction decreases more. Okay, so we have, in this case, our endothermic reaction is the reverse. So what happens is it decreases more than the forward because it is the endothermic reaction. So both would decrease, endo and exo. So exo decreases that much, but the endo decreases more because in this case, the endo is the reverse. And then whichever one is higher and lower, they always meet in the middle to re-establish equilibrium. Okay, somewhat like that. Okay, so both reaction rates decrease. Again, if you have any questions, please ask. I hope that this is making sense. Okay, so when there's a decrease in temperature, always for rate of reaction graph, both reaction rates decrease, but the endothermic reaction decreases more. And that's why in this case, we decrease the rate of the reverse more than the rate of the forward. And it forms what somewhat looks like a dead duck. Okay, so in this case, you can remember it by understanding, you can remember this by remembering that the endothermic reaction, let's just get rid of this arrow. The endothermic reaction for temperature change rate versus time graph, the endothermic reaction is always affected more. So it either increases more, okay, or in this case, it decreases more. Okay, let's move on to the next one. Concentration versus time. Now, for rate versus time graph, when there's an increase in concentration. Now, remember, this was an increase in concentration of N2. All right, it was a reactant. Okay, so what happens is the following. Okay, the concentration of the reactant increases. That's true, right? The concentration of N2 increased. Okay, the concentration of the reactant increased. Okay, so since the concentration, let's look here, since our concentration of one of our reactants increased, remember, according to Le Chatelier's principle, the other side is favored. So therefore, it says here that the rate of the forward increases. The rate of the forward increases. Okay, so that's the first thing we should note. Whichever one there was an increase in concentration of, that rate is the only one that increases immediately. Okay, so in this case, there was an increase in concentration of N2, which favored the forward reaction. Therefore, the rate of the forward increases. Okay, that's you'll see that these concentration versus time graphs are easy to identify. You'll see why in a bit. Okay, so again, increase in concentration of N2 according to Le Chatelier's principle, the other side is favored. In this case, increase in concentration of a reactant would favor the forward reaction. So since the forward reaction is favored, right, because of this understanding, the forward reaction is the only reaction that increases rapidly immediately. Okay, and that's it. Then what happens is they re-establish equilibrium. So they meet again in the middle somewhere to re-establish equilibrium. Okay, just pretend that that's equidistant. And that forms what somewhat looks like a big head duck. Okay, somewhat, again, I'm not an artist. Okay, just a way to remember it. Okay, so yes, in this case, there was an increase in concentration of N2, which is a reactant. We know according to Le Chatelier's principle, that favors the forward reaction. Okay, the forward reaction is favored. So the reaction that is favored immediately, that would result in a rapid increase in its rate. Okay, and then they reestablish equilibrium. Okay, the reason, this is a further explanation as to the reason why the rate of the reverse eventually increases is because the concentration of the product therefore increases and therefore the rate of the reverse increases. Actually, I don't think that's too important for now. It's okay. We can just understand that they reestablish equilibrium. Okay, the important thing to note here is that the concentration of, the important thing to note here is that the concentration of the reactant increases, therefore the rate of the forward rapidly increases. Let's add the word rapidly. Okay, rapidly increases, and that gives us our graph. As we can see, the rapid increase in the concentration of, the rate of the forward reaction. That's because the reactant increased. Okay, now let's have a look at it for this one. The rate of reaction, the rate versus time graph when there's a concentration decrease. Again, this is a concentration decrease of N2, which is a reactant. Okay, so let's copy this here. So this says the concentration of the reactant decreases, therefore the rate of the forward decreases. The rate of the forward decreases. That's how it's affected. The concentration of the reactant decreases. Okay, we know that N2 is decreased. So since, remember, according to Le Chatelier's principle, the concentration of the reactant decreases, that favors the same side. So it would favor the reverse. Okay, but the way we look at it for rate versus time graph is that the concentration of the reactant decreases, therefore the rate of the forward reaction immediately is the one that decreases. Oops. There we go. Okay, so immediately the rate of the forward reaction decreases, and that's all. They thereafter rejoin to establish equilibrium. Sorry, there we go. Okay, they thereafter rejoin to re-establish equilibrium. Okay, at T3, forming a big head dead duck. Okay, so just remember what? Remember that the concentration of the reactant decreases, therefore it results in the rate of the forward reaction, okay, rapidly decreasing. Okay, which is important for us to understand, and that's why we have a rapid decrease in the forward reaction and the reverse reaction. Then they just meet again to form equilibrium. That's the easiest way to remember it. Okay, so you'll see that the temperature graphs, they always have this like long extra piece here where both reaction rates are affected. And you'll see with pressure, it's the same, but with concentration, only one rapidly increases and then the other catches up, or only one rapidly decreases and then the other catches up. Okay, so you can see big head ducks, if you will, if you want to remember it that way. Okay, but yes, for that's the distinguishing characteristic of the concentration versus time graph. Okay, and then this should be fine without it. I'll decide whether to put it in later or not, but it should be fine without it. Okay, so I hope that makes sense. Concentration versus time graph. The reactant, whichever compound increases or decreases, that the reaction that it affects either increases or decreases respectively. Okay, so in this case, we increase the concentration of a reactant. Therefore, the forward reaction, its rate increases rapidly. Okay, because now you have extra reactants. So the forward reaction needs to be favored to use up those reactants to form products. Okay, then we have a decrease in concentration of a reactant. Therefore, we have a decrease in the rate of the forward because now we have less reactants to form products. Okay, so that's a different perspective. That's how we should look at it. Okay, always. So that's okay. That's, you see, again, that's a different type of way to look at the rate versus time graph. It's not, it doesn't maybe follow the logic that you might expect. Okay. Now let's do the final one, pressure change. Okay, rate versus time graph. When there's an increase in pressure, by the way, by a decrease in volume, increase in pressure by a decrease in volume, okay, what happens and which rates are affected? We have it written here, okay. According to this thingy, both reaction rates increase, but the reaction which is favored increases more. So that's a simple one. Both reaction rates increase, but the reaction which is favored increases more. Let's try and remember which reaction is favored. An increase in pressure by a decrease in volume, if I remember correctly from TCP, favors the less mole side. In this case, the less mole side is the products. If you want to favor the products, you will have to favor the forward reaction. So in this case, the forward reaction is favored first. So the forward reaction is favored. Forward is favored. So both reaction rates increase, but the reaction which is favored increases more. So the forward increases more. That's pretty simple. Forward increases more compared to the reverse. Why? Because it is favored. So the forward increases that much, the reverse increases, let's just say that much, and then they meet again to re-establish equilibrium. Okay, and again, we have a duck. So as you can see, the temperature increase and the pressure increase. Well, for this specific question, they look the same. Okay, so you need to be careful. There'll be other things that would help you identify whether it's temperature or pressure. But concentration is easy to distinguish because of its big head. Okay, so let's look at it. So yeah, both reaction rates increase, but the reaction rate which is favored increases more. Then we can have a look at a pressure decrease. Okay, a decrease in pressure, by the way, by an increase in volume, don't forget that. A decrease in pressure by an increase in volume, according to Le Chatelier's principle, would favor the more mole side. Okay, so therefore it's going to favor which side? It's going to have to favor the reactant side, and the reactant side is favoring the reverse. So both reaction rates decrease. Okay, look at this one carefully. Both reaction rates decrease, but the reaction rate that's favored decreases less. The reaction that is favored, the reaction that is favored decreases less. Both reaction rates are both reaction rates decrease, but the one that favored decreases less. That makes sense. So in this case, both would increase, okay, but the one that is favored increases more. Both decrease, but the one that's favored, because it's favored, meaning it occurs more, okay, it would decrease less. So in this case, we know that which one is favored. We know that here the reverse is favored. Why? Because we know that the more mole side is favored and the reactants have more moles, so the reverse is favored. Okay, the reverse is favored, so both reaction rates decrease, but the one that's favored decreases less. So in this case, the one that decreases more is the one that's not favored, and that's the forward reaction. So the forward reaction decreases more, reverse reaction decreases less, simply because it is favored. So then they reestablish equilibrium. They meet again in the middle in order to reestablish chemical equilibrium. Let's do this. Let's do that. Nope. Nope. Let's do that. And that's somewhat acceptable. And again, we have a dead duck. Okay, so please keep that in mind. For this one, both reaction rates increase, but the one that's favored increases more. And that's for this one. But for this one, both reaction rates decrease, but the one that's favored decreases more. So please, that applies for pressure changes on a rate versus time graph. Very important stuff. Okay, as well as concentration, temperature. So you can see how these graphs are slightly a lot different actually compared to the concentration versus time, and how each one has their own specific rules that they need to follow. Okay, so that's graphs done, right? Again, I hope you guys understand. What I left here is from Science Clinic. It's a nice summary, okay, for, I think it contains every single possibility. So you can go through it, see if there's anything you don't understand, okay? But for the example we went through, it's for this specific equation, all the possibilities, increase, decrease, increase, decrease, increase, decrease, 6 times over. And this is it for another chemical reaction, okay, all the different possibilities. So you can go through that with explanations, okay, on each one. So concentration, explaining what happens on each graph. Okay, so you can go through this as a nice summary to recap. Okay, it's a really nice summary to recap what happens each time. Okay, now let's move on to discuss KC calculations. Okay, so what we're going to do is we're going to discuss KC and perhaps try out a question and then hopefully get to the explanation. Even if we do take a bit of extra time, I would like to finish these 2 pages and then maybe have a last, I don't know if we have the time actually, because we still need to do acids and bases, which is a last topic. Let's see, right? Do a question, maybe if I have to do an extra lesson. I know I've been telling you guys I want to do an extra lesson, it just hasn't happened. But yeah, to do an actual a full question and with graphs and everything, but let's see if time allows us, if time permits, right? But obviously you guys should be practicing on your own either way, and you can message if you have any questions or need any help. Now, let's get to KC and let us discuss what is KC. Okay, give me like 30 seconds. Okay, cool. Now, KC, all right, let's go through the concept of KC. So KC basically is an equilibrium constant, okay? So KC itself, what it means is it is an equilibrium constant. It is the equilibrium constant. Okay, and essentially what it is, okay, it is the ratio of the concentration of products over reactants at equilibrium. Okay, it is the ratio, okay, of the products, the concentration. So these square brackets, always remember square brackets here in chemistry. These square brackets represent concentration. Okay, so they're not there for no reason. They're telling us that it's actually the ratio. Ratio is represented by the fraction, by the way. Okay, that tells us it's a ratio. And it is, again, a ratio between the concentration of the products over the concentration of the reactants at equilibrium. Okay, so not just initially, okay, whatever the concentration of the products are at equilibrium, we take it and we divide it by the concentration of reactants at equilibrium as well. Okay, so that's what this is. Equilibrium, KC is an equilibrium constant. Okay, and also because it's a constant, we need to remember it has no units. Okay, it's not moles or anything like that. It has no units because it's a constant, right? It's a ratio. Sorry, not a constant, it's a ratio. It's like a 5-to-1 ratio, whatever it is. So you're saying like, okay, we have 5 times the amount of products and we have compared to reactants. So we have 1/5 of the product compared to reactants, like a ratio. Okay, that's all it is. So when we have a high KC, that means we have a high yield. And when we have a low KC, that means we have a low yield. Now remember the word yield represents the amount of products formed. Product formed. Okay, that's what yield tells us. It's the amount of product that we formed. So of course, a high KC, right, means that we have a high amount of products. And when you have a higher numerator compared to a denominator, that results in an overall higher value. For example, if I have 5/10 compared to 15/10, which one is a bigger number? This is 1/2, and this is 3/2. Okay, so this is actually 0.5. And this is 1.5. So clearly a higher numerator results in an overall higher value. Always remember that a higher numerator results in an overall higher value, and a higher denominator would mean a lower value. So high KC comes from having a high numerator, which means high products, which means high yield. Okay. And high KC, okay, generally refers to a KC greater than 1. okay? And a low Kc generally refers to a Kc less than 1, okay? Because greater than 1 would mean more products than reactants, okay? And less than 1 would mean more reactants and products, okay? So a Kc greater than 1, high Kc with a high yield, okay? High amount of products formed. Low Kc, less than 1, low yield, low amount of products formed. Okay. Another thing to note, which is very muy importante, okay, about Kc, where can I write it? I normally write it like somewhere here. Okay, is that Kc is not in, is only affected by one thing, and that is temperature. There is nothing else that affects Kc except temperature. Kc is only affected by temperature, okay? So you can only change Kc if you change temperature. Maybe let's add that in. Kc can only be changed if the temperature is changed. It's essentially saying the same thing. Okay, so you see those questions where they try to trick you. Okay, they'll tell you a catalyst is added. How does that affect Kc? No effect. Okay, why? Because the only thing that changes Kc is changing the temperature. Okay, so Kc can only be changed if the temperature is changed. Okay, so let's have a look at this. Now, these are, if the forward reaction is favored, that's an increase in temperature. And then if the reverse reaction is favored, that's a decrease in Kc, sorry. Okay, but okay, in order for the forward reaction to be favored, we have to make a temperature change. That's the key thing here. So by altering temperature, if the forward reaction is favored, that would result in Kc increasing. Okay, and by altering temperature, if the reverse reaction is favored, that would decrease Kc. So not just all the time when the forward is favored, Kc increases. Only if the forward is favored due to a change in temperature, whatever it is, whether it's an increase in temperature or a decrease in temperature, it doesn't really matter. Okay, as long as we change the temperature, increase or decrease, and it favors the forward, Kc is going to increase. And as long as we change the temperature, increase or decrease, and the reverse is favored, that would result in a decrease in Kc. Right? Remember, changing temperature doesn't directly affect forward or reverse specifically. What does it affect? Changing temperature affects endothermic and exothermic. So depending whether the endo or exo is forward or reverse, that just depends on the question and the chemical equation specifically. That would then result in the forward or reverse being favored, and therefore Kc increasing or decreasing. Okay, so just keep that in mind. Kc is only affected by temperature. Kc can only be changed if temperature is changed. Okay, and by altering temperature, if the forward is favored, Kc increases. Okay, and by altering temperature, if the reverse is favored, then Kc decreases. Okay, quite simple. Another thing to note, okay, is that if we have, and I'm just going to steal an equation here, the only concentrations that we consider for Kc, the only concentrations at chemical equilibrium that we consider for Kc is that of gases and aqueous is that of gases and aqueous solution. In order, you'll see, we're going to do an example of a KC calculation now in a second, okay? And we always take the concentration at equilibrium. We always take the concentration at equilibrium, and we do not consider anything but a gas and an aqueous solution. If it's a solid, okay, we don't consider it. Okay, so let's do a quick demonstration. Let's just say we have a chemical equation that has 5A, and it's a solid, plus 3B gas, okay, which gives us C aqueous plus 2D gas. Okay, let us, okay, that should be fine. It would be nice if it wasn't so big, but it's fine. Let's do this. Let's change the color of all of this too. Right, okay. So, yes, just pretend that A, B, C, and D are chemical symbols for any chemical compound or element from periodic table, okay? But we just refer to them as A, B, C, or D. Now, we have molar ratios given. 5A, which is a solid, gives us 3B gas, okay? Sorry, 5A plus 3B, which is a gas, gives us C, which is aqueous, and 2D, which is gas. Now, we are going to formulate a KC equation. Okay, so KC, remember, it is equal to the concentration of the products over the concentration of the reactants. But there's one thing we need to note, okay, is that it is to the power of the molar ratio. We always add its molar ratio as an exponent. We always add the molar ratio as an exponent. We always add the molar ratio as an exponent. Okay, it doesn't exactly fit there, but it's fine. We always add the molar ratio as an exponent. Okay, so in this case, it's the concentration of the products divided by the concentration of the reactants. Okay, and that's going to give us our KC ratio. But we need to use the molar ratio, each molar ratio here, that 5. Okay, that one we won't consider, I'll tell you in a bit. 3, that 1 in front of the C, and the 2 in front of the D. Okay, so in this case, we're only going to consider B, C, and D. Why? Because for KC, we only consider what? We only consider gas and aqueous. We don't consider any solids. Okay, so now we're going to use the concentration of the products. So it's going to be C, the concentration of C, of course, at equilibrium, to the power of 1. Okay, now we don't just have one product, we have two products, so we multiply it by, always multiplication, the concentration of D to the power of its molar ratio, and its molar ratio is 2, so it's to the power of 2. So the concentration of C times the concentration of D to the power of its molar ratio, divided by the concentration of the reactants, and we only take in consideration gas and aqueous, so the only gas one that we have is B. So the concentration of B to the power of its molar ratio, which is 3. There we go. Okay, so Kc is equal to the concentration of the products divided by the concentration of the reactants. And if there are multiple products, we multiply, or multiple reactants, we multiply each concentration and we put it to the power of its molar ratio always. Okay, so that's an example of how we conduct it. Let us finish this example. So an example, 3 moles of NO2 okay. Let's not finish this example because I just realized it requires us to do a YC table. Okay, so let's not finish it because it will take quite a long time and I don't want to not do it properly. We rather take the time. So we're definitely going to have another lesson of this. I'm going to try and organize an extra lesson for you guys to complete acids and bases as fast as possible. If we can maybe do an extra lesson for the rest of the month, that would be excellent so that we can catch up with the acids and bases very quickly. Okay, cool. Okay, so yeah, because we are currently behind. Okay. Perfect. Okay, so let us end it there. I'm going to leave the thing open for the next 5 to 10 minutes. Please, if you guys have any questions, any confusions, let me know. Then we can address them right here. Even if you'd like to unmute your mic, okay, I can allow you to talk and you can unmute your mic and ask the question like with your mouth, with your words. Okay, you don't have to type it, and I can try and re-explain something to you. Okay, so you can tell me, listen, uncle, I'm not an uncle, don't call me uncle. I don't understand pressure change. It didn't make sense. I don't know what you're waffling about. Please just explain to me how both reaction rates increase, but the one reaction which is increased is favored more, whatever, anything. Okay, so yeah, it's going to be open for the next 5 to 10 minutes. For those of you who have any questions or even want to stay to listen to if anyone has any questions, you are free to. For those of you who need to leave, you are free to leave. Thank you guys so much for joining. Jazakallah khair. I will see you guys next week. Assalamu alaikum and goodbye. But yeah, again, to reiterate, it will be open if for those of you who have any questions. Is the Kc value affected by the solid? Nope. And I'll tell you why the Kc. So it's only affected by two things, which is gas or aqueous. And that's why in this case, we didn't even consider the solid at all. And you'll see sometimes in questions, you won't even be able to calculate the concentration of the solid. And that's not a problem because you don't need to. And the reason it is because you can't really measure concentration of a solid. Okay. Whenever it comes to concentration, you don't really consider a solid. Okay, and if I'm not mistaken, if we see for TCP, when we discuss TCP, right, remember for concentration, we also said gas or aqueous only, because again, concentration of a gas, concentration of aqueous, we cannot consider the concentration of a solid. Okay, so even for TCP, we only did that. So the same thing applies for Kc. Kc is not affected by the concentration of a solid, so you don't even consider it. No problem, you're welcome. While you guys are here, can you guys please tell me what topic you guys are currently doing at school? Are you guys okay? So first, before you tell me what topic are you currently busy with, are you guys done in school with acids and bases? I'm guessing that you are. Are you guys done with acids and bases? Yes, no. Most of you should be done. Okay, cool. So what topic are you guys currently busy with? For those of you who are completed with acids and bases, maybe electricity or motors and generators or photoelectric effect. What topic are you guys currently busy with? Electricity. Okay, cool. Electrochemistry, damn, okay. And electricity. Okay, cool. That's fine. We're probably going to do electricity next, because that's what the plan says, that you start off with electricity. Then it's in that plan that I sent you guys, or that's in the Google Drive, electricity, then electrodynamics, then photoelectric effect, then electrochemistry. But yeah, we are kind of like behind, like very behind, because we're still busy with a term 2 topic, and then we still have another term 2 topic. So I'm definitely going to arrange a second lesson for you guys. I'm going to try my best to do that, so that we can try and finish up like very fast, so we can start acids and bases and start electricity at the same time. So we'll have one lesson a week. This is the plan. Hopefully we'll have one lesson a week for acids and bases, and one lesson a week for electricity, obviously, until we're done with both. And then once we caught up, we can see if we still need those extra lessons, we can use them, or if not, we can just continue with the singular lesson. Yeah, that would be nice. But yeah, okay. If there's no further questions, let us end it there. Okay. And thank you guys so much for joining. Good luck. I know that most of you are starting school tomorrow. All the best. And yeah, let us like try and make the next 2 blocks, the next 2 terms better than the first 2 terms. Obviously, I don't have to tell you guys are in grade 12, you know the importance of your marks, especially if you want to study, or especially if you want to pass. Okay. So I would recommend this is now the time where you should start working hard. Okay. And you can still, even if you haven't been working hard for the first half of the year, or if your marks have been slacking, you still have a lot of time to catch that up. So now it's a great opportunity to start now and to make sure that all your SHIT is in order and that you can get the marks that you want to achieve. Okay, start practicing, start doing past papers. Okay, it's not too late. Trust me, if you feel like it's too late, you have a lot of time. Okay, and yeah, I wish you guys good luck. Have a good week at school, and I will be in contact with you guys hopefully in the week or today or tomorrow, whatever, with regards to the extra lesson and anything else that's relevant. And I will see you guys next week. Please make sure we keep up this attendance. Okay, it's important, right? We don't want these lessons to end. So yeah, cool. Thank you guys again so much for joining. I will see you guys next week. Jazakallah khair. Assalamu alaikum.